In this lesson, I'll show you how to solve exponential growth and decay problems with differential equations. This is question number 3 in the series. The question reads, the rate of change of the amount of morphine in the human bloodstream is proportional to the amount of morphine present. If initially there is 0.4 milligrams of morphine in the bloodstream and only 0.2 milligrams remain after 3 hours, find an equation for the amount in the bloodstream at any time. I'm going to start off by letting A equal the amount of morphine in the bloodstream. I'll write that down. And by doing this, my equation will be A at t. And by taking the derivative of A of t, I end up with A prime, and A prime can be written as dA over dt, is equal to a constant of proportionality, which I'll represent with the letter K, multiply to A. Next, I'll find the general solution of this differential equation. And I can do that by separating the dA and the dt on either side. I'll dedicate the right side to dt and the left side to dA. And it's totally random which side you choose. I'll start by multiplying both sides by dt. This cancels out the dt on the left side, and now it's on the right side, and I'll divide both sides by k times a. This gives me dA over k times a is equal to dt. Now that dA and dt are on the top level of each of these fractions, I can integrate both sides. I'll integrate this side and this side. Of the two, dt is easier to integrate. It simply becomes t plus c, our constant. And on the left side, I can pull out 1 over k, given that it's also a constant, a number. And integrating dA over a gives us ln absolute of a. I'll next multiply both sides by k to clear the denominator on the left side. This goes away, and we're left with kt plus c. No need to put a k in front of the c. Remember, I want my equation as a of t. So my next step is to get rid of this ln, and I can do that by raising both sides of this equation to the base e. Given that ln is equal to log base e, this goes away, leaving us with the absolute of a on the left side and e to the power of kt plus c on the other side. Instead of writing e to the power of kt plus c, I can write it as e to the power of kt times e to the power of c. I'm just using the laws of exponents here. Remember that if the bases are the same, you can add the exponents and you end up with the same thing. I do not want absolutes on the left side. So to get rid of this absolute, I'll just write it as a is equal to, and instead of the absolute, I'll make note that the right side needs to be plus minus. So plus minus e to the power of kt e to the power of c. E to the power of c, along with this plus minus, can be replaced with another letter. Let's call it m. So we have a is equal to m times e to the power of kt. This is a very important equation that we just came up with. And let's go back to our question. We're told that initially, so when a is equal to 0, we have 0.4. Then, 3 hours later, this part, so our t here is in hours, a of 3 is equal to 0.2. I'm going to go ahead and substitute 0 and 0.4 into my growing equation. That way I can find out what m is equal to. So I'll replace this a with 0.4, and I will replace this t with 0. This gives me m times e to the power of k times 0. That's the same thing as e to the power of 0, and anything to the power of 0 is equal to 1. Therefore, m is equal to 0.4, and we have come up with our equation. Our equation is a is equal to 0.4 e to the power of kt. To find out what this k is, I can now replace this point, where this 3 goes into the t, this part goes into my a, and I can find out what k is. I have 0.2 is equal to 0.4 e to the power of k times 3. Solving for k isn't hard. I'll divide both sides by 0.4. And then, to get k, I'll ln both sides. So I'll ln this, and I'll ln this. Watch what happens. This K3 goes to the front, and ln E becomes 1. So I have this expression on the left side, where 0.2 over 0.4 is equal to half. So I'll replace that with ln half. K times 3. Dividing both sides by 3 gives me ln half over 3 is equal to k. I'll replace this expression for k into my equation that I wrote earlier, which looks like this. Let's go ahead and do that. We have a is equal to 0.4 e to the power of what I have for k, which is ln 1 over 2 t over 3. Notice that I put this 1 over 3 underneath the t. And if you simplify this further, e ln 1 over 2 becomes simply 1 over 2. I'm using the laws of exponents here. A is equal to 0.4 times 1 over 2 raised to the power of t over 3. This right here represents a function in terms of t for the amount of morphine in the bloodstream at any given time. And there you have it. That is how to solve exponential growth and decay with differential equations.